This problem will be basic orbits in Kepler number 7. We have Saturn. Here it is. Saturn. Big planet. Rotating. And it rotates with some period t. I'm going to call it t because that's going to be the period of a satellite existing out here that's orbiting Saturn in such a way that it stays at one location above the surface of Saturn all the time. So as Saturn orbit rotates once, the satellite goes around once. So if you're a little Saturnian, you on your little hind legs here looking up into the sky will see this satellite in the same place all the time. It'd be a little bit difficult because you'd sink into the gas and get killed first, but nevertheless, it's a thought experiment. So here's our satellite with period t, and our goal is to find r, the orbital radius, equivalent to the distance to the center of Saturn. So I'm going to say a day. It talks about a day for time, and that's equal to the period of rotation or the period of orbit. So we start with our basic concept that Fc is equal to Fg. The centripetal force needed by the satellite to go into the orbit that's required is provided by gravity. And since we have the period, we don't have the speed, we're going to use the period form of centripetal force. M, 4 pi squared r over t squared is equal to big G, big M, little m, over r squared. Now this is little m here. This is big M. And little m goes away. And so I need to solve for r, so let's get it by itself. I'm going to cross multiply. 4 pi squared r cubed is equal to G, big M, t squared. Solving for r is equal to G, M, t squared over 4 pi squared to the 1/3 power. That's it. I guess I could stop right now, but what I'm going to do is go ahead and put some numbers in, some example numbers, just to make sure we know how to do the details here. So 6.67 times 10 to the negative 11. That is universal gravitation constant. The mass of Saturn, 5.68 times 10 to the 26th. T squared, I had 10.66 hours, so that'd be 10.66 times 3600 seconds per hour. I'll just write that there because this time has to be in seconds, and that's squared. This whole thing divided by 4 pi squared. The whole thing, whoop, taken to the 1/3 power. Oh, okay, it's off the screen here. There it is. This whole thing to the 1/3 power. Plugging all this into the calculator, I get r, the radius of orbit, 1.12 times 10 to the 8th meters. That's how you do the problem. Wasn't that fun?